Okay, so welcome to the first lecture that we have in this coronavirus era. As I mentioned before, all of the lectures are going to be online now, and most of them, or all of them, should be in this format, where I'm going to do the lecture on my iPad and then I'll upload it to Titanium. So we have 3 more lectures to go. We have Lab 4, Lab 5, and then Lab 6. So today's Lab 4. And this is going to be for aerodynamic forces on immersed bodies. So for this lab, basically what we're going to do is we're going to use a low-speed wind tunnel. And we're going to put some objects in there and we're going to find the lift and drag on these objects. So let's specifically write out the goals for this experiment. Okay, so I've written out all the goals that we have for this experiment. We have quite a lot here that we have to do. So the first one, we want to look at the drag force on a sphere and a hemisphere. Next one, we want to measure the lift and the drag force on an airfoil with different slat and, that should say, flap configurations. And then we want to do that at different angles of attack. And we want to look at the surface pressure distribution over an airfoil and a cylinder. And then we're going to measure the lift and drag on a small scale fighter jet plane. Okay, so let's start to go over the theory. Okay, so the main part of this experiment is lift and drag. So you guys have probably touched on this in your fluids class, but we'll go into more depth for this lecture here. So first I'll write out lift and drag are aerodynamic forces that act on a body moving through a fluid medium. Okay, so for our experiment, we're going to be using a fluid medium of air. So basically what we'll see is that this wind tunnel, it's a low-speed wind tunnel. It's basically a large Venturi meter. So think of the first lab that we did, but in this case, it's going to be really big compared to that. And instead of water, we're going to be using air. Okay, and then the two forces that we're going to be looking at in this lab are lift and drag. So lift, that's going to be normal to the flow. And then our drag is going to be tangential to the flow. Tangential to the flow. Okay, and then these forces, they're generated from pressure and shear stress distributions over the body. So I'll put generated from pressure and shear stress. And then just as with the lift and drag, the pressure is going to be normal to the surface and the shear stress is going to be tangential to the surface. So what we'll see is that this pressure is going to create lift on our object, and then the shear stress, that's going to be the drag that's on the object. And it's from the shear stress that we have, or the viscosity that we have, that creates drag, and then that's when we have this pressure difference on our object, and then that's going to create our lift because of that pressure difference. Okay, so again, we're going to be using a low-speed wind tunnel, so I'll quickly draw this out right now. Okay, so it's going to look something like this. Again, it's basically one big Venturi meter that we have. So we're going to have our inlet here. We're going to have flow going into the inlet. And then in the back here, we have a fan that's connected to a motor. And basically this fan is going to draw the air into the system from the ambient atmosphere, and then it's going to exhaust it out this outlet where the fan is at. Okay, so then we'll have station 2. This will be the test section. So in this section you might have your airfoil. We're going to be testing an airfoil, and then our fighter jet model. So we're going to have these things in the test section. And then we're going to have the diffuser. Okay, so we have that, and then the final one is just station 4, where we're going to exhaust back into the atmosphere. So we have station 1, and this is going to be at an inlet that's pretty big, and you'll see in the inlet that we're going to have this kind of honeycomb pattern, and what that is going to do is straighten out the flow for us. And then we're going to converge to the test section, so our airspeed is going to increase, and then we're going to diverge, and the diffuser is going to decrease and then go out into the atmosphere. Okay, so let's talk about lift and drag now. Okay, so we already covered that these aerodynamic forces, they're going to act on a body as it moves through a fluid medium. So in our case, we're using the wind tunnel. Our objects aren't going to be moving through that medium, but we're going to have airflow around it. So we have that, I guess, that kind of reference frame. So we can still find the lift and the drag on our object because we still have some airflow in the system. Okay, so there are 2 ways that we can find the lift and drag. So we'll say for a body in free stream conditions, and that means V infinity, rho infinity, and P infinity. Then we can find the aerodynamic forces using either 2 methods. One is a force-sting balance, and the other is integrating the pressure distribution over the body. Okay, so once we actually go to our lab, what you'll see is we'll go into the wind tunnel, and in there we're going to have a device that basically is going to give us the drag and the lift values that we have. We're going to basically see the force that it's applying on the object. So then we'll get the lift and the drag according to which direction that force is coming from. And then what we're going to do for the sphere and hemisphere, and I'll talk about this a bit later as well, we're going to have these objects, and there's going to be holes that are drilled into it, and they're going to be connected to static pressure taps. And then from that, we're going to find the coefficient of pressure for that. Okay. So now I'm going to draw an airfoil, and then we'll talk about the orientation for a lot of these things. So for the lift and the drag and the free stream velocity, and then the angle of attack. Okay, so I've drawn out an airfoil here, and then if we have a free stream velocity, so this is coming in at V infinity, this is going to hit our airfoil, and this line here that I've drawn in red, this is going to be called the chord line. So this line is going from our leading edge straight to the trailing edge. And this angle that the free stream velocity is going to make with the chord line is the angle of attack. Okay, and we denote the angle of attack as alpha. Okay, so now let's talk about the forces here. We already said that lift is going to be normal to the flow. So here we have the force of our lift, and then drag is tangential to the flow. So we have our drag right here. Okay. So I think I mentioned this before, but basically what we're going to be solving for a few of the data reduction questions are the coefficient of lift and drag. So let's write this out, and we'll talk about how to solve for it. Okay, so our lift coefficient, that's going to be C sub L, or CL, whatever. And we'll write this out as CL is equal to our lift divided by 1/2 rho infinity V infinity squared times A. Okay. So FL, that's going to be the lift, or the lift force. Rho infinity, that's our free stream velocity, or density, sorry. Then V infinity, that's the free stream velocity. And then A is going to be our area. And for this, it's going to depend on what object we're measuring. So for an airplane wing, that's going to be the planform area, or basically the area that you see for the wing if you're looking straight down on it. And then for a sphere, it's going to be the cross-sectional area. So we'll say for a wing, that's our planform area. And then for a sphere, cross-sectional. Okay, so that's our lift coefficient. Now let's do the drag coefficient. It's going to be pretty much the same thing, but just for drag. Okay, so for that, it's just going to be the force of our drag divided by 1/2 rho infinity V infinity squared times A. And then we'll also take note that 1/2 rho infinity V infinity squared, that's our dynamic pressure. Okay, so let's look at these formulas and let's think about how we can find them in the lab. So I'll just do this for the coefficient of lift. So the lift force, we can find that in the lab. Again, we're going to measure that directly. So we'll have that value. Rho infinity, we'll know that. We can look at the temperature of the air and then we can find the density. The planform area or the cross-sectional area, depending on the object, we can measure that and find that. And then the free stream velocity, we don't know that right away, so we're going to have to find that. And basically what we're going to do is the same thing as in the second experiment for the air duct. We're going to use a pitot tube, in this case a pitot-static tube, and we're going to be able to find that air velocity. And then once we do that, then we can find our lift coefficient and our drag coefficient. Okay, so now we're going to talk about airfoil nomenclature. Okay, one of the things we'll be testing in this lab is an airfoil. So we need to know the geometry definitions. Okay, so here I have my airfoil. And then what I'll do here is I'll draw the chord line. So we talked about this chord line before. So that's going to be a straight line from our leading edge to the trailing edge. Okay, so let's label this. This is the chord line. And then, so really, okay, that's the chord line, but really the distance from the leading edge to the trailing edge, that's going to be the chord. So for that, I'll write it down here. So the chord C is the distance from the leading edge to the trailing edge, where LE and TE mean leading edge and trailing edge. Okay, so now let's talk about the camber line. Okay, so pretend that I drew this correctly here. The camber line is going to be the locus of points between the upper and lower surfaces of the airfoil. So think of it as it's the midway point at each point on the airfoil. So if I go to this point right here, pretend that that is in the middle between this point up here and this point down here. And then we'll keep doing that as we go along our x-axis. Okay, so that's the camber line. And then what we have is this distance in between the camber line and the chord line, that's called the camber. Okay, so really I should draw this maybe right here. That's going to be the maximum distance that we have from the camber line to the chord line. Okay, so that's going to be at one kind of plane. Okay. And then the last thing we have to talk about is the thickness. So that should be pretty self-explanatory here. That's just going to be the distance from the upper and lower surface measured perpendicular to the chord line. So that's one thickness right there. And here's another thickness right there. So our thickness is going to change as we go along the airfoil. Okay, so make sure you just get a little familiar with that so you know what you're talking about in your lab report. Okay, so as we discussed earlier, one of the things we need to find before we can find the drag and lift coefficient is the local airspeed. So again, this is going to be pretty similar as to what we did in lab 2. So in lab 2, we used a pitot tube and a manometer to measure the local airspeed. So the pitot tube, that measured the stagnation pressure, and then we had a static port on the side of our air duct, and that went to a manometer, and we combined those two things to have our stagnation pressure and our static pressure, and then we could find the local airspeed in the duct. So we're doing a very similar thing here, but instead of using a pitot tube, we have a pitot-static tube. So this static port is included on this pitot tube. So once we use this, again, we're going to find the stagnation pressure and the static pressure, and then we can find our local airspeed in the system. Okay, so what I've done now is I've imported this picture because I don't want to draw it. So basically we have a pitot-static tube here. So it looks like our pitot tube that we had in the last experiment, or in experiment 2, except this time we have these static pressure ports that are circled in purple. So we're going to measure the static pressure, and then we're also going to measure the stagnation pressure. So this static pressure comes in a tap, and it's going to come along on these outer walls. And that's where we're going to measure that static pressure. That's going to go to a manometer as well. So how do we find the airspeed? So recall from experiment 2, to find the airspeed, we used this formula. Okay, so our local airspeed is going to be given by the square root of 2 times the stagnation pressure minus the static pressure all over the air density. So in experiment 2, we used vertical manometers. In this case, we're not going to use vertical manometers, we're going to use an inclined manometer. And the reason for this is we're not going to have a very big difference in our water height. So we still want to have some good resolution. So what we do is we use an inclined manometer. And that way, even if there's only a small pressure difference, that water height or that water level is still going to rise a lot because it's inclined instead of completely vertical. So this way we can have better accuracy or better resolution for these pressure differences, even though they're still pretty small. Okay, so our manometer is going to look something like this, where we have P1 at station 1, and then we have P2 at station 2, and then this angle at the horizontal, that's going to be theta. And if I fill this with some water and we get this height difference, that's going to be h. And then let me draw a line here. Okay. And then that distance right there, that's going to be L. So it's this kind of distance along this line that we have for our height difference. Okay, and then our pressure difference, we know this, it's just going to be a hydrostatic equation. So we have P1 minus P2 is equal to rho GH, where in this case rho is going to be rho of our gauge fluid, the density of the gauge fluid. What we've typically been using in our experiments was water. This time, one of the stations will have water and the other is going to have oil. They both might have oil this time. I'm not sure if they're kind of updated to that, but we'll see when we get there. Okay, and then for our height, we can find that with a formula. So that's just going to be the height equals delta L times sine of theta. So delta L, that's just going to be L. We have that difference in length. We basically just need to look at that length reading, and then we can find that. Okay, so knowing these variables, we can now rewrite the hydrostatic equation that we just had. So we can now write this as P1 minus P2 equals the density of our gauge fluid times the gravity times delta L sine of theta. Now remember, we want to find the local airspeed, so we're going to plug in P1 minus P2 into our formula here for the local airspeed. So we're going to plug that in to this formula here. Okay, so we can do that. But let's first note that P1 minus P2, that's going to be equal to P stagnation minus P static. Okay, now we can plug it into that formula for the airspeed. Okay, so there we go, got that box now. So we have the airspeed is equal to, this should be the square root of 2 times the gravity multiplied by the density of the gauge fluid over the density of air times delta L sine of theta. So now we can find our local airspeed, and then we can go ahead and find the coefficient of drag and coefficient of lift. Okay, so we'll do a little recap on specific gravity, because remember, we're not going to be using water for our manometer, or it's very likely that we're not. We're going to be using oil that's dyed red. So for that, we're going to need to find the density of this oil. So to find the density, we're going to look at specific gravity. Okay, so let's first define what specific gravity is. That's going to be the ratio of the density of the gauge fluid to the density of water at 4 degrees Celsius. Okay, and then I'll note here the density of water at 4 degrees Celsius is 1,000 kilograms per meter cubed. Okay, so for the experiment, one of the stations, it might be water that's dyed green, though I think this was the case for a few years ago, and it's since been updated to oil. But if you have a wind tunnel that has water that's dyed green, then your specific gravity, that's just going to be 1, because we have the density of water divided by the density of water. However, if you have a wind tunnel that has oil that's dyed red, which should be the case, that specific gravity is going to be 0.826. So what we can do now is we can modify our equation to find the local airspeed. Okay, so let's go ahead and modify our formula. So this one here, we'll now see that the airspeed is equal to 2 times the gravity times the specific gravity of our gauge fluid multiplied by the density of water at 4 degrees Celsius divided by the air density times delta L sine of theta, and that's going to be the square root. Alright, so let's box this one now. Made a square, force. Okay. Alright, moving along here, slowly but surely. We'll talk about drag measurement corrections. Okay, so basically what we have is the objects that we're putting in our wind tunnel, they're going to be mounted on a support rod. So what's happening is we're getting the drag on the object, but we're also getting drag on the support rod. So really, if we're looking at our reading for the drag or the lift, we're getting that total drag and that total lift. Well, we don't want that, so what we have to do is put in our object on the support rod at one point, and at a different point in time, we're only going to put in the support rod. And that way we can find the drag on that support rod, then we can subtract it out. Okay, so to do this, what we're going to have is this equation where the drag force, the net drag force, is equal to the total drag force minus the offset drag force. Okay, so the net drag force, that's going to be the drag on our body of interest. The total drag force is going to be the drag on the body of interest and the support rod. Okay, and then the offset drag force, that's going to be just the drag on the support rod. Okay, so we can do that, and then we can find just the drag on our specific body of interest, whether that's an airfoil or like the small little fighter jet model. So with this in mind, we can rewrite our drag coefficient that we had from earlier. Okay, so we're going to have the coefficient of drag is going to be equal to our net drag force, or the drag on the body of interest, divided by 1/2 rho infinity v infinity squared times our specific area for the body. Remember, that might be the planform area for a wing, or it'll be the cross-sectional area for a sphere. Okay, so now we'll talk about high lift devices. So first off, for a given airfoil and Reynolds number, the maximum lift coefficient, CL max, is going to be a function of the airfoil shape. So if you have an airfoil and a wind tunnel, and that's all you have, then the maximum lift coefficient that you can have on that, it's just going to depend on the airfoil shape that you have. So this is an issue that a lot of people want to overcome for, flying real planes. So what we do is we use trailing edge flaps and leading edge slats. And basically this will alter our geometry and flow patterns a bit, and then we can adjust our lift coefficient. And then in this way we can increase our theoretical maximum lift coefficient. Okay, so what I've done now is written out quite a lot of stuff. So for the trailing edge flap, that's going to be a portion on the trailing edge of our wing, and I can have it go up or down. I can deflect it up or down from a hinge. So if I deflect it down, I'm going to increase the camber of the airfoil, and then I'm going to effectively increase the theoretical coefficient of lift. Then if I deflect it up, I'm going to decrease the camber, so I'm going to decrease the theoretical lift that we have. Then for a leading edge slat, this is going to be a thin curved surface that's deployed in front of the leading edge, and this is going to allow secondary airflow to enter through a gap between the slat and the airfoil leading edge. So let's take a look at these. So here's a picture of different configurations. So in figure A, we're just cruising, so our leading edge slat is closed and the trailing edge flap that's closed as well. And then for B, what we have is the leading edge slat that's open. So we're taking off here, so we're increasing our angle of attack because we want to have more lift. So we're opening up this flap, and I'll talk about these pressure gradients in a second. But we're also decreasing the trailing edge flap, so we're increasing the camber. So we're increasing that maximum lift that we can have. Then if we look at station or picture C, what we've done here is we're deflecting our trailing edge flap. Okay, that's going to go down at the end. So what we have now is more force going down once we're landing on the runway. So our lift is going down basically. Then we're going to be braking on the runway. And the last picture here, and if you see for that, we have our trailing edge flap up. So what we're doing now is we're slowing down. We basically have air brakes with that flap there. Okay, so hopefully that kind of made some sense, and we could go into more detail, but you'll also see how these flaps and slats affect the lift in the experiment as well. So they're pretty cool, and if you're on an airplane and you're taking off or landing, you can see them moving around as well. They're used very often. Okay, so for this leading edge slat, I also wrote that if it's open, it's going to mitigate an adverse pressure gradient on the top surface, and it's going to delay flow separation and increase the stall angle of attack, and then increase our lift coefficient as well. So basically, when we're taking off, like in picture B, we want to increase our angle of attack. But again, our geometry for the airfoil, that's kind of limiting us for our maximum our maximum lift. So we're going to use our high lift device to increase that maximum lift. That's when we use this leading edge slat. However, once we're increasing our angle of attack, at some point we're going to increase this angle of attack too much, where the top flow, it's going to become detached from our airfoil. It's not going to be able to curve around as it should, like this in red. It's going to detach. And from that detachment of the airflow, we're going to have, it's called airflow separation. And then from that, that's going to lead to stall. So basically, we don't want to stall out, of course. So what this does when we have this slat is we're increasing our maximum lift coefficient, so we can have more lift and also delay this flow separation because we're allowing some airflow to come in through the slat. Okay, so hopefully that made sense as well. And there's some cool fluid videos for flow separation that you can look up as well, and you can kind of get a better feel for how this occurs once we start to increase the angle of attack. Okay, so the last thing we have to talk about, I know it's been a pretty long lecture here, it's a pretty long lab, so we have a lot to talk about. So we'll discuss the surface pressure distribution. Okay, so as we said before, one of the ways that we can find aerodynamic forces is by integrating the pressure distribution that we have over a surface of our body of interest. Okay, and then we're going to express this pressure distribution also as a coefficient, in this case the pressure coefficient. Okay, so we're finally on the last topic for this lecture. We talked about quite a lot of stuff in this lab. It is a pretty long and complicated lab, so there's a lot to discuss. Okay, so the surface pressure distribution. So if you remember earlier in this lab or in this lecture, we talked about how we could find aerodynamic forces by integrating the pressure distribution over the surface of a body of interest. So for example, if we knew the pressure distribution on the surface of an object and the shear stress, then we could integrate those, and then we could find the lift and the drag force that way. In the case of our lab, we're going to express this pressure distribution in terms of the pressure coefficient. Okay, so the pressure coefficient, Cp, this will be equal to the pressure at some point, the static pressure, minus the free stream pressure, over 1/2 rho infinity V infinity squared. So again, P infinity, that's the free stream pressure, and then P is the local static pressure. Okay, and then I'm also putting right there on the surface of the body. So remember, for our lab, we're going to be looking at a hemisphere and a sphere, and for those, we're going to have holes that are drilled into the surface. So these holes, they're going to be our local static pressure taps. So this pressure tap, though, it's going to be equal to the pressure at the surface at the point of interest. And because of that, once we go in the lab, you got to make sure that the surface on these objects are very smooth. So we're sure that that pressure on the surface is going to be the static pressure at that hole. Okay, so I'm not going to write that part down, just something to note though. Okay, and then for all of those static pressure taps that we have, they're going to be connected to a manometer. Okay, so they're connected to a manometer, and the opposite end of the manometer is going to be open to the atmosphere. Okay, so then we can find the static pressure on the surface of the body as P surface, again that's the static pressure, that's going to be equal to our atmospheric pressure minus rho GH. Okay, so that's just our hydrostatic equation kind of rewritten. So again, we have the density of some gauge fluid, and I think that should be oil as well, though we'll be sure once we get to the lab. Okay, and then H, that's going to be the vertical displacement of the gauge fluid inside the manometer, as we know from past experience. Okay, and then if the manometer that we're using is inclined, then we're going to have P surface is equal to the atmospheric pressure minus the gauge density times the gravity. Sorry for the Reddit notification. Times the gravity times delta L times sine of theta. Okay, and then so we can get our surface pressure using this method or the other method, depending on the type of manometer that we're using. Okay. Last thing we have is measuring the free stream static pressure. Okay, so to measure this, we're going to use a pitot tube and a manometer again. So our pitot tube, that's going to be in our test section, and we're going to have a static port that's connected to a manometer, and then the other end of the manometer is going to be open to the atmosphere. So for this, all we have is P infinity equals the atmospheric pressure minus the density of the gauge fluid times gravity times delta L sine of theta. So it's basically the same as the equation that we just wrote above, but in this case our pitot tube, that's going to be used for the atmospheric pressure, and it's not going to be a tap, that's connected on the surface of our sphere or hemisphere. Okay, so now you have that, and you should have everything that you need for this lab. If you have any questions on the theory for this lab, then let me know before we go to the lab, and I can help you out. So I know this was a long lecture. Again, it's a long lab, but it is a pretty fun lab from what I remember, so hopefully you've learned something, and hopefully you're excited for the lab as well. And I'll see you guys then.